With many tasks in the real world, a great technique for completing them is to break them into more easily accomplishable parts. Even mathematicians use this technique, and that's what we will be learning today. Hi, my name is Jason Rosenberry, and today we'll be investigating integration by parts, so let's take a look at that formula. Integration by parts formula. The integral u dv can be rewritten as u times v minus the integral v du. This formula expresses one integral, the integral u dv, in terms of a second integral, the one that is integral v du. With proper choice of u and v, the second integral may be easier to calculate than the first. In making these choices, we want u to be something that simplifies when differentiated, and dv to be something that remains manageable when integrated. So here's a strategy for choosing the proper u. We use the abbreviation LIPIT. LIPIT means that when you're ready to choose something for u, you should try to choose in this order. First, you should be looking for natural logarithm. If you don't have that, then look for inverse trig functions. And then if you don't have those, choose a polynomial function. If not that, then followed by exponential function, and then finally trigonometric function. Let's try an example. Find the indefinite integral. We have the integral x sine x dx, and we want to evaluate this integral using integration by parts. So using the LIPIT strategy, we're going to try to choose a proper u. So the first letter in LIPIT is L. Do I have any natural log functions in my integral? No, I do not. I stands for inverse trig functions. Yes, I have a trig function, sine x, but we're to look for inverse trig functions second. Don't have that. P in LIPIT, polynomial function. And I do have a polynomial function right here. Y equals x is a polynomial function. So we're going to let u be x. And then we will let dv be the rest of the integrand. So dv would equal sine x dx. Now we want to differentiate u and integrate dv. So if u is x, then du is the derivative of x, which is just 1 dx. And now we'll integrate dv to get v, and the antiderivative of sine x dx is negative cosine x. Now that I have u, dv, du, and v, we can substitute those values into the integration by parts formula. So by using this formula, let's rewrite the original integration problem using our integration by parts formula. So this would be equal to u times v. U is x and v is negative cosine x. So we'll have x times negative cosine x, or negative x cosine x, minus the integral v du. V du would be negative cosine x dx. Negative cosine x, that's v, and du is dx. And this integration problem is much easier than the original. So now we're ready to find the final answer. So this is equal to the negative x cosine x. And now let's evaluate this integral. Well, we can pull this negative sign out, and with this negative sign creates positive, and then the antiderivative of cosine x dx is just sine x plus some constant c. So the final answer is negative x cosine x plus sine x plus c. Sometimes we need to use integration by parts multiple times in order to evaluate an integral. Find the indefinite integral. We have the integral x squared times e to the x dx, and using the LIPIT strategy, let's try to find a proper expression for u. I have no natural log functions. I have no inverse trig functions. Again, I do have a polynomial function x squared, so we'll start with that. Let's let u be x squared. Therefore, dv is the remainder of the problem, e to the x dx. We will now integrate dv. So v, the antiderivative of e to the x dx, is e to the x, and we will differentiate u. du is equal to 2x dx. We'll now use our integration by parts formula to rewrite the original integration problem as u times v, x squared times e to the x is x squared e to the x, minus the integral v du. v du would be e to the x times 2x dx, and I'm going to rewrite that integral like the following. It's going to give us x squared e to the x minus this factor of 2 we can pull out in front of the integration symbol, and that means we're left with x e to the x dx. So believe it or not, we must use integration by parts a second time so that we can evaluate this integral. So let's use the Lipit strategy again to choose a correct expression for u for our next integral situation. So let's let u equal x. Therefore, dv is the rest of the integration, the integrand, e to the x dx. So now we will integrate dv. So therefore, v is e to the x, and du would equal 1 dx. So now let's just worry about what this part of the problem is, just this part of the problem. That portion of the problem, using integration by parts, would be u times v. u times v would be x e to the x minus the integral v du, and v du would be e to the x dx. And again, just simplifying that portion, we would have x e to the x minus, and now our third integration that we have to take care of is an easy one. The antiderivative of e to the x dx is simply e to the x plus some constant, which we'll take care of that at the end of the problem. So we're going to go ahead and now substitute this expression in for the box that we had up here. So making that substitution, we now have 2 times the quantity x e to the x minus e to the x. Now don't forget your plus c, your constant at the end of your indefinite integral, and now we'll just distribute the negative 2 through the parentheses. So we have x squared e to the x minus 2x e to the x plus 2e to the x, and then we have a plus constant at the end. This technique works for any integral, the integral x to the n e to the x dx, in which n is a positive integer. Because differentiating x to the n will eventually lead to 0, and integrating e to the x is easy. Now let's turn our attention to solving for an unknown integral. Use integration by parts, and solve for the unknown integral. Let's say that we're given the following problem, the integral e to the x sine x dx. Using the Lipit strategy, we will let u equal e to the x. Therefore, dv will be sine x dx. We'll now integrate dv, giving us v is equal to negative cosine x. And we will differentiate u, giving us du to be e to the x dx. Using our integration by parts, formula, we can now write our problem as u times v, which would be negative e to the x cosine x, multiplying u times v together, minus the integral v du. So it's negative cosine x. However, that negative I'm going to pull out in front of the integration sign, and it'll make that a plus. So we have cosine x, and now I need du, which is e to the x dx. E to the x dx. We will now use integration by parts a second time on this integral. Using the Lipit strategy, we will let u be e to the x. Dv would be cosine x dx. V would equal sine x. And du would be e to the x dx. So again, we will use integration by parts a second time, and I'm simply going to, what I write from this point, I'm simply going to evaluate what this integral would be, and then I'll make the substitution. So just this integral, using integration by parts, again is u times v, so that would be e to the x sine x. There's u times v, minus the integral v du, so that would be sine x e to the x dx. I'm now going to substitute this expression in here for that integral. I'm going to rewrite that all out. So making that substitution, here we have the current equation. And I want you to notice that we end up with the same integration problem on both sides of the equation. So I'm going to take this term to the other side, giving us two of them. So we now have 2 times the indefinite integral of e to the x sine x dx equal to what's left with the right hand side, which is negative e to the x cosine x plus e to the x sine x. And now we can simply divide both sides by 2. So the problem that we started with, which is the integral e to the x sine x dx, is equal to the right hand side, negative e to the x cosine x plus e to the x sine x all over 2 plus some constant c. Let's examine tabular integration. Evaluate x squared e to the x dx. Again, using the Lipit strategy, we would have chosen u to be x squared and dv as being e to the x dx. And to tackle this integration problem using a tabular approach, start with your x squared, start with u, and then differentiate until you get to 0. Take dv, which is e to the x dx, just think about the e to the x portion, and keep integrating. So the antiderivative of e to the x is e to the x, etc., etc., etc. And then to get your final answer, start with the upper left-hand corner, x squared, and pair that up with a diagonal lowering by 1, e to the x. So we're going to multiply those together to get x squared e to the x, and the first product, start that off as being a positive product. So we would start off with x squared e to the x. And then notice from this point on, your signs will always alternate, positive, negative, positive, negative. So we'll grab the next two, which is 2x and an e to the x, and we'll write that as minus 2x e to the x. Go down to the next product, which is positive 2 times e to the x, positive 2 times e to the x, and now we're finished because we've gotten to 0. And the only final step would be to add c onto the end, and as you can see, we get the same solution as we did earlier with this same problem. Next, we will explore the antiderivatives of the logarithmic and inverse trig functions. Find the antiderivative, or the integral, natural log x dx. So using our lipid strategy, let's let u be natural log x. Therefore, dv is what's remaining, which is simply dx. We now integrate dv. So the antiderivative of dx would be x, and the derivative of u, or du, the derivative of natural log x is 1 over x. Using integration by parts formula, now we can write our original problem as u times v. U times v would be x natural log x minus the indefinite integral v du. V, which is x, times du. Oops, I forgot the dx. Du is 1 over x dx. And look what happens right here. X times 1 over x gives us 1. So we currently have x natural log x minus the antiderivative of simply dx. So our final answer would be x natural log x minus the antiderivative of dx is just x, and then we have a constant on the end, plus c. Now it's time for inverse trig functions. Find the indefinite integral of inverse cosine of x dx. So using lipid strategy, let's let u be the inverse cosine of x, and we'll let dv be dx. That implies that v is equal to x, and the derivative of u, the derivative of the inverse cosine of x, is negative 1 over square root of 1 minus x squared dx. So now using integration by parts formula, we'll rewrite our original problem as u times v. So that would be x times inverse cosine x minus the integral v du. So v du, combining those together, would be negative x over the square root of 1 minus x squared dx. So now to evaluate this indefinite integral, we will use substitution. Let's let u be 1 minus x squared, which implies that du would be equal to negative 2x dx. So take a moment and look at du. I need x dx, which I already have. There's x, there's dx. There's a negative sign, which I already have. I'm just missing this factor of 2, so you know the trick. We'll put a factor of 2 here, which then in part puts a factor of 1/2 out in front of the integration sign. So in doing so and using u substitution, we get the following equation, the following expression. So we now have the equation. This is equal to, the original problem is equal to x inverse cosine x minus 1/2 times the integral u to the negative 1/2 du. And we can quickly evaluate this integration. So we currently have x times the inverse cosine of x minus 1/2 times the following. It would be u to the 1/2 over 1/2 plus a constant that we'll add to the end. And now notice what happens when we simplify. This 1/2 multiplied by 2, dividing by 1/2 is the same as multiplying by 2, would actually multiply by this 1/2, causing 1 to happen, a factor of 1. So that leaves us with x times the inverse cosine of x minus, right now we are left with u to the 1/2 power, but now we're going to unsubstitute. Remember that u is the same thing as 1 minus x squared. So here we would have u to the 1/2, which is the same thing as the square root of 1 minus x squared. And then we have plus c, our constant at the end. Now it's time for you to try a problem. Find the indefinite integral inverse sine x dx. Pause the video while you work on this problem. When you are finished, restart the video to check your solution. So using the Lippitt strategy, we'll let u equal the inverse sine of x, dv will equal dx, v equals x, and du is 1 over the square root of 1 minus x squared dx. So now we'll substitute those into the integration by parts formula, and that gives us u times v, or x times inverse sine x, minus the indefinite integral of v du. v du would be x over square root of 1 minus x squared dx. And again, like last time, to evaluate this integral, let's use u substitution. So we'll let u equal 1 minus x squared. Therefore, du is negative 2x dx. We have the dx, we have the x, we need a negative 2. So if we're putting a negative 2 up here, causes me to write a factor of negative 1/2 out here in front of the integral. And I'll make those substitutions now with our u substitution. So making that substitution gives us x times inverse sine x plus 1/2 times the integral u to the negative 1/2 du. And now it's time to simplify this integration step. So we have x inverse sine x plus 1/2 times, here we would have u to the positive 1/2 over 1/2 plus c that I'll add to the end of the final answer. And again, notice that this factor of 1/2, which would, if we multiply by 2, we end up with a factor of 1. So our final answer ends up being x times the inverse sine x plus 1 times u to the 1/2. Well, u is the same thing as 1 minus x squared. So we get the square root of 1 minus x squared. So there's my u to the 1/2, and then plus c, our constant. In this section, we explored product rule in integral form, solving for the unknown integral, tabular integration, as well as logarithmic and inverse trig functions. Make sure you work the problems your teacher assigns, and we'll see you next time.